In the stillness of deep space, where light travels for billions of years before reaching our instruments, something unexpected has emerged from the data streams of the James Webb Space Telescope. Something that whispers of galaxies forming in an epoch when the universe should have been too young, too chaotic, too formless to allow such structures to exist. If you're watching, consider full screen, and subscribe to follow this journey. The discovery speaks to galaxies that appear fully formed, blazing with starlight, existing merely 300 million years after the Big Bang, a time frame that challenges the carefully constructed models cosmologists have built over decades of observation and theory. This is not a story of distant abstractions, but of fundamental questions about how matter organizes itself in the aftermath of creation, how gravity pulls hydrogen into clumps dense enough to ignite, how those first stars then seed the formation of larger systems, and how all of this unfolds on a clock that may tick faster than anyone predicted. To understand why these galaxies represent such a profound puzzle, we must first reconstruct what we thought we knew about the early universe, beginning with the moment when time itself became meaningful. The Big Bang was not an explosion in space, but an expansion of space, a sudden inflation of the fabric of reality carrying with it all matter and energy in a state of unimaginable density and temperature. In those first moments, the universe was opaque, a seething plasma, where particles collided with such fury that photons could not travel freely, scattering endlessly through a fog of charged particles. This era, known as the photon epoch, lasted for hundreds of thousands of years, during which the universe was essentially a furnace, too hot for atoms to hold together, too violent for structure to form. The temperature was millions of degrees, dropping steadily as space expanded, stretching the wavelengths of radiation, and allowing the energy to dilute across an ever-growing volume. As the universe cooled, protons and electrons finally combined to form neutral hydrogen atoms in a process called recombination, occurring roughly 380,000 years after the Big Bang. This event marked the release of the cosmic microwave background radiation, the afterglow we still detect today, a faint whisper of that ancient fire now stretched into microwave frequencies by the expansion of space over nearly 14 billion years. With recombination, the universe became transparent for the first time, allowing light to travel unimpeded, and this moment is often described as the surface of last scattering, the farthest back we can see with photons, because before this point, photons were trapped in the plasma, unable to carry information across cosmic distances. Yet the universe after recombination was not immediately filled with stars and galaxies. Instead, it entered a period cosmologists called the Dark Ages, an era lasting perhaps several hundred million years when the universe was filled with neutral hydrogen gas, slowly expanding and cooling with no sources of light except the fading glow of the Big Bang itself. The gas was not perfectly uniform, though. Tiny fluctuations in density, imprinted during the inflationary epoch in the first fractions of a second, served as seeds for structure. Regions that were slightly denser than their surroundings had slightly stronger gravitational fields, pulling in more matter from the surroundings, growing incrementally denser over time. This process is known as gravitational collapse, and it operates on a timescale determined by the balance between gravity's inward pull and the thermal pressure of the gas pushing outward. The first structures to collapse were small, perhaps only a few million times the mass of the Sun, far smaller than modern galaxies. As these clumps of gas contracted under their own gravity, they heated up, converting gravitational potential energy into thermal energy. In the centers of the densest clumps, where pressure and temperature climbed highest, conditions eventually became extreme enough to ignite nuclear fusion, the process by which hydrogen nuclei combined to form helium, releasing energy. This was the birth of the first stars, population 3 stars in the terminology of stellar astrophysics, massive objects composed almost entirely of hydrogen and helium because the universe had not yet synthesized heavier elements. These stars were likely enormous, perhaps hundreds of times the mass of the Sun, burning fiercely and living for only a few million years before exploding as supernovae, scattering newly formed heavy elements into the surrounding gas and providing the raw material for the next generation of stars. The epoch of the first stars, known as the Cosmic Dawn, is believed to have begun somewhere between 100 and 200 million years after the Big Bang, though pinning down the exact timing has been a central challenge in cosmology. The light from these first stars began to ionize the surrounding neutral hydrogen, carving out bubbles of ionized gas that gradually expanded and merged, a process called reionization that eventually rendered the entire universe ionized once again, though now at a far lower density and temperature than the primordial plasma. Reionization is thought to have been largely complete by around 1 billion years after the Big Bang, but the exact timeline depends critically on when the first stars formed and how efficiently they produced ionizing radiation. Galaxies, as we understand them, are not simply collections of stars, but complex systems bound together by gravity, with stars, gas, dust, and dark matter interacting in intricate ways. The formation of a galaxy requires not just the collapse of gas into stars, but the assembly of multiple such regions into a coherent structure, held together by a shared gravitational potential well dominated by dark matter. Dark matter, which does not emit or absorb light but interacts only through gravity, is believed to make up roughly 85% of the matter in the universe, and its gravitational influence is essential for pulling ordinary matter into the dense concentrations needed to form galaxies. The current paradigm, known as the lambda cold dark matter model, or lambda CDM, posits that structure in the universe forms hierarchically, with small dark matter halos collapsing first, then merging over time to build progressively larger structures. In this hierarchical framework, the first galaxies were small and faint, forming in the densest regions where dark matter halos collapsed early. These proto-galaxies were sites of intense star formation, but they were also relatively inefficient at converting gas into stars because the energy released by supernovae and stellar winds could blow gas out of the shallow gravitational wells of small halos, quenching star formation. Over time, these small galaxies would merge, growing into larger systems, and the process of merging and accretion would continue over billions of years, eventually producing the massive galaxies we see in the local universe today. According to this model, the universe at 300 million years after the Big Bang should have been in the very early stages of galaxy formation, with only small, faint protogalaxies beginning to assemble, still in the process of building up their stellar populations and mass. The lambda CDM model has been remarkably successful at explaining a wide range of observations, from the distribution of galaxies on large scales to the patterns in the cosmic microwave background. It has been refined through decades of work, with precise measurements of cosmological parameters such as the Hubble constant, the density of matter, the density of dark energy, and the amplitude of primordial fluctuations. Simulations based on lambda CDM can reproduce the large-scale structure of the universe with impressive fidelity, showing the cosmic web of filaments and voids, the clustering of galaxies, and the formation of massive galaxy clusters. These simulations rely on vast computational resources and sophisticated physics, tracking the evolution of billions of particles from the early universe to the present day, accounting for gravity, gas dynamics, star formation, supernova feedback, and the growth of supermassive black holes. Yet, for all its successes, lambda CDM makes specific predictions about the early universe that can be tested observationally, and it is here that the James Webb Space Telescope has introduced a surprising tension. The predictions concern not just when the first stars formed, but how quickly galaxies could assemble significant stellar mass. The formation of a galaxy with billions of stars requires time, not just for stars to form but for supernovae to enrich the gas with heavy elements, for multiple bursts of star formation to occur, for gas to cool and settle into a disk or other organized structure. Each of these processes operates on a certain time scale, and when you add them up, standard models suggested that galaxies with substantial stellar masses, comparable to those of modern galaxies, should not appear until several 100 million years after the Big Bang at the earliest, and more realistically not until closer to 1 billion years. The critical tool for probing the early universe is the redshift, a measure of how much the wavelength of light has been stretched by the expansion of the universe during its journey from source to observer. When a galaxy emits light, that light travels through expanding space, and as space expands, the wavelengths of the photons are stretched proportionally. This stretching shifts the light toward longer wavelengths, toward the red end of the spectrum, hence the term redshift. The amount of redshift, usually denoted by the symbol Z, is directly related to the scale factor of the universe at the time the light was emitted compared to now, and through cosmological models, it can be converted into a look-back time, telling us how long ago the light was emitted, and thus how old the universe was when the galaxy we are observing existed. A galaxy at a redshift of Z equals 1 corresponds to a look-back time of about 8 billion years, meaning we see the galaxy as it was 8 billion years ago when the universe was less than half its current age. As redshift increases, we look further back in time, and the relationship becomes increasingly steep. A redshift of Z equals 6 corresponds to a universe roughly 1 billion years old, while Z equals 10 takes us back to around 500 million years after the Big Bang. Observing galaxies at even higher redshifts, Z greater than 10, pushes into the first few 100 million years of cosmic history, the era when the very first galaxies were forming. These are the most distant objects in the universe, and their light has been traveling for almost the entire age of the cosmos to reach us. The challenge of observing such distant galaxies is formidable because their light is not only faint due to distance, but also shifted far into the infrared part of the spectrum. A galaxy emitting ultraviolet and optical light in the early universe will have that light red shifted into near-infrared or even mid-infrared wavelengths by the time it reaches us. Ground-based telescopes struggle with infrared observations because Earth's atmosphere absorbs and emits infrared radiation, creating a bright and noisy background that overwhelms faint cosmic sources. Space-based telescopes avoid this problem, and the Hubble Space Telescope made significant strides in detecting high redshift galaxies using its infrared instruments, pushing detections out to redshifts around z=10 or slightly higher. However, Hubble's infrared capabilities were limited by the size of its mirror, 2.4 meters, and the sensitivity of its detectors, restricting its ability to find and characterize the faintest and most distant galaxies. The James Webb Space Telescope, launched in December 2021 and beginning science operations in mid-2022, was designed specifically to overcome these limitations. With a primary mirror 6.5 meters in diameter, nearly 3 times the diameter of Hubble's and with almost 6 times the collecting area, Webb gathers far more light, allowing it to detect much fainter objects. Its instruments are optimized for infrared wavelengths, covering a range from about 0.6 microns at the red edge of visible light, out to 28 microns in the mid-infrared, a range perfectly suited for detecting the red-shifted light from the earliest galaxies. The telescope's location at the second Lagrange point, a gravitationally stable position about 1.5 million kilometers from Earth on the side opposite the Sun, allows it to maintain a stable thermal environment with the Sun, Earth, and Moon all on one side behind a large sun shield, keeping the instruments cold and minimizing thermal background noise. Webb's instruments include the near-infrared camera, or NIRCam, the primary imaging instrument capable of capturing wide-field images in several infrared filters, the near-infrared spectrograph, or NIRSpec, which can obtain detailed spectra of hundreds of objects simultaneously, and the mid-infrared instrument, or MIRI, which extends observations into longer wavelengths. These capabilities allow Webb not only to find distant galaxies, but to characterize their properties in detail, measuring their brightness at multiple wavelengths, obtaining spectra to determine precise redshifts and study the physical conditions in the gas, and mapping the spatial structure of these early systems. Even before the formal start of science operations, during the commissioning phase when the instruments were being tested and calibrated, Webb began returning images that hinted at the unexpected. The early release observations, a set of images and data released to the public in July 2022, included a deep field image of a galaxy cluster known as CAG 0723, showing thousands of galaxies in exquisite detail, many of them gravitationally lensed by the foreground cluster, their light magnified and distorted. Among these galaxies, astronomers immediately noticed objects that appeared to be at very high redshift based on their colors, the way their brightness dropped sharply at certain wavelengths, a signature of the Lyman break, the absorption of ultraviolet light by neutral hydrogen along the line of sight. Some of these objects had colors consistent with redshifts of z greater than 10, potentially placing them in the first 400 to 500 million years after the Big Bang. Initial photometric redshifts, estimates based on the brightness in different filters, suggested redshifts as high as z=12 or even higher, pushing into an era cosmologists had barely begun to explore. As Webb science programs commenced, multiple teams began systematically searching for high redshift galaxies using deep imaging surveys. One of the first major findings came from a program called the Cosmic Evolution Early Release Science Survey, or CEERS, which observed a region within the extended Groth strip, a field previously studied by Hubble. The CEERS images revealed a population of bright red objects with photometric redshifts, suggesting they lay at c greater than 10. One candidate, initially dubbed Maisie's Galaxy, after the daughter of one of the astronomers on the team, showed a photometric redshift of about z=11.8, implying an age of around 330 million years after the Big Bang. Spectroscopic follow-up later confirmed a redshift of z=11.4, still placing it in the very early universe, only about 370 million years after the beginning. Other surveys quickly followed with similar discoveries. The GLASS or Grism Lens Amplified Survey from Space, and its successor GLASS JWST used gravitational lensing by foreground galaxy clusters to magnify distant galaxies, allowing Webb to detect even fainter objects. The JDIS survey, a large program using both imaging and spectroscopy, found multiple galaxies with spectroscopic redshifts greater than z=10, with some candidates pushing toward z=13 or higher. One object, JDIS GSCZ130, was confirmed with a spectroscopic redshift of z=13.2, corresponding to a universe only about 320 million years old. Another candidate from a different survey, initially reported as potentially at z=16 or even higher, generated intense discussion in the community, though subsequent analysis suggested a somewhat lower, though still very high, redshift. What made these discoveries particularly striking was not just the redshifts themselves, though those were impressive, but the properties of the galaxies. Based on their brightness and estimated distances, astronomers could calculate their luminosities, the total amount of light they were emitting, and from that infer their stellar masses, the total mass of stars they contained. The calculations depended on assumptions about the stellar populations, the mix of star ages and masses, and the amount of dust obscuring the light. But even with conservative assumptions, the inferred stellar masses were surprisingly large, often in the range of billions of solar masses. For comparison, standard models predicted that galaxies in this era should have stellar masses, more like millions or at most tens of millions of solar masses, orders of magnitude smaller. The tension becomes clearer when considering the time available for star formation. At a redshift of z equals 13, the universe is only about 320 million years old. If the first stars began forming at, say, 150 million years after the Big Bang, that leaves only 170 million years for a galaxy to assemble its stellar mass. Star formation is not instantaneous. It proceeds at a certain rate, measured in solar masses per year, and that rate is limited by how quickly gas can cool and collapse, how efficiently it can form stars before feedback processes blow the gas away, and how much gas is available in the first place. Typical star formation rates in modern galaxies range from a few solar masses per year in the Milky Way to hundreds in extreme starburst galaxies, but even at a very high rate of, say, 100 solar masses per year, building a billion solar mass galaxy would take 10 million years of continuous star formation at that rate, and sustaining such a high rate for so long in such a small young system is challenging. Moreover, the stellar mass we observe is only the end product of star formation. Much of the mass that goes into stars is later lost through stellar winds and supernovae, returned to the interstellar medium rather than locked up in long-lived stars. The efficiency of star formation, the fraction of gas converted into stars that remain bound to the galaxy, is typically thought to be relatively low, perhaps 10 to 30% in small early galaxies. This means that to build a galaxy with a billion solar masses of stars, you might need several billion solar masses of gas to start with, and that gas must have been assembled into the dark matter halo, cooled, and formed stars all within a few 100 million years. The problem is compounded by the fact that the galaxies Webb is finding are not just massive but also bright, and in some cases relatively compact, suggesting they have already undergone significant evolution, perhaps multiple generations of star formation. Their spectra, when obtained, show emission lines characteristic of hot gas being ionized by young stars, and the strengths of these lines provide clues about the stellar populations and the ionization state of the gas. Some of the galaxies show signs of enrichment with heavy elements, oxygen, carbon, nitrogen, indicating that supernovae have already exploded and seeded the interstellar medium with the products of nucleosynthesis, a process that itself requires time because the massive stars that produce these elements live for only a few million years. So detecting heavy elements means that star formation has been ongoing for at least 1 or 2 generations of stars. The standard hierarchical model of galaxy formation, built on lambda CDM cosmology, predicts a bottom-up assembly process where small structures form first and merge to build larger ones. In this picture, the first stars form in small dark matter mini-halos, with masses around 1 million solar masses, and these mini-halos then merge to form larger halos over time. The growth of structure is regulated by the expansion of the universe and the initial spectrum of density fluctuations, which is characterized by a power spectrum with more power on small scales than large scales at early times, meaning small structures collapse first. The timeline for assembling a galaxy with a given mass depends on the initial fluctuations, the dark matter density, and the rate at which halos merge. Simulations of structure formation in a lambda CDM universe show that dark matter halos capable of hosting galaxies with stellar masses of 1 billion solar masses should not be common at redshifts much higher than z equals 10, and even those that do exist at such high redshifts have only recently assembled from smaller halos, meaning their constituent gas has only recently begun to form stars. The simulations predict that the stellar mass function, the distribution of galaxy stellar masses, should be steeply declining at high masses and high redshifts, with very few massive galaxies present in the early universe simply because there has not been enough time for hierarchical assembly to build them. Yet Webb's observations suggest a stellar mass function that is higher than predicted, with more massive galaxies present at high redshifts than the simulations produce. One way to quantify this tension is through the concept of the cosmic star formation rate density, the total rate of star formation per unit volume of the universe at a given cosmic time. This quantity can be measured observationally by detecting galaxies at different redshifts, measuring their star formation rates, and integrating over the population. It can also be predicted from models of galaxy formation. Prior to Webb, Observations with Hubble and other telescopes had measured the star formation rate density out to redshifts of about z equals 8 to 10, and the measurements showed a gradual decline as redshift increased, consistent with the idea that the universe was progressively younger and had had less time to form stars. Extrapolating this trend suggested that the star formation rate density should continue to decline at higher redshifts, dropping significantly by z equals 13 or 15. However, Webb's observations suggest that the star formation rate density may not decline as steeply as expected, or may even remain relatively high at redshifts greater than 10. The discovery of numerous bright, actively star-forming galaxies at these high redshifts implies that star formation was more vigorous or more widespread in the early universe than standard models predicted. This could mean that the initial conditions for star formation were more favorable than assumed, that feedback processes were less effective at quenching star formation, that the efficiency of converting gas into stars was higher, or that some other physical process not included in current models played a significant role. Another aspect of the puzzle concerns the luminosity of these early galaxies. Luminosity is related to the number and brightness of stars, which in turn depends on the stellar mass and the age distribution of the stars. Young, massive stars are very bright, especially in the ultraviolet, while older, lower-mass stars are much fainter. If a galaxy is actively forming stars, it will have a population of young, bright stars and will be luminous. If star formation has ceased, the galaxy will fade as the massive stars die off. The galaxies Webb is observing are quite luminous in the rest frame ultraviolet, indicating active star formation, but their luminosities are higher than expected for galaxies of their inferred stellar masses based on typical assumptions about star formation histories. This suggests either that the star formation rates are extraordinarily high, exceeding those seen in local starburst galaxies, or that the stellar populations are unusual, perhaps with a top-heavy initial mass function, meaning a higher proportion of massive luminous stars compared to low-mass stars than in modern galaxies. A top-heavy IMF would produce more light per unit stellar mass, making the galaxies appear brighter and potentially leading to an overestimate of stellar mass if standard IMF assumptions are used. Alternatively, the galaxies might be experiencing a particularly intense burst of star formation, a phase that might not last long but could temporarily boost the luminosity significantly. Disentangling these possibilities requires detailed modeling of the spectral energy distributions, comparing the observed brightness at different wavelengths to predictions from stellar population synthesis models. The spectral energy distribution, or SED, is the distribution of a galaxy's light across different wavelengths, from ultraviolet through optical to infrared. For high redshift galaxies, the observed SED is shifted into the infrared, and by measuring the galaxy's brightness in multiple infrared filters, astronomers can reconstruct the rest frame SED and compare it to models. The models depend on assumptions about the star formation history, the age of the stellar population, the metallicity, the amount of dust, and the IMF. By adjusting these parameters, one can fit the observed SED and derive estimates of stellar mass, star formation rate, age, and other properties. However, these fits are often degenerate, meaning multiple combinations of parameters can produce similar SEDs, and small changes in assumptions can lead to significant changes in derived quantities. Dust, in particular, introduces uncertainty. Dust grains composed of silicates, carbon, and other materials absorb and scatter ultraviolet and optical light, then re-emitted in the infrared. A galaxy with significant dust will appear redder and fainter at short wavelengths than a dust-free galaxy with the same stellar population, and the infrared emission from dust can dominate the SED at longer wavelengths. In the local universe, many galaxies are dusty, and the amount of dust generally correlates with metallicity and star formation rate because dust is produced by stars and supernovae, and star-forming regions tend to be dusty. However, in the very early universe, there has been little time for dust to form, so the first galaxies might be expected to have low dust content. If that is the case, the observed SEDs should be relatively blue and unobscured, but some of the Webb galaxies appear redder than expected, raising the possibility of significant dust even at these early times, which would imply rapid dust production and a more evolved stellar population. The presence of dust at high redshifts also affects the interpretation of emission lines in spectra. Lines such as hydrogen alpha, the line and alpha transition of hydrogen, and lines from oxygen, carbon, and other elements are used to probe the physical conditions in the gas, the star formation rate, the ionization state, and the chemical composition. If dust is present, it can absorb some of the line emission, making the lines appear weaker than they actually are and leading to underestimates of, for example, the star formation rate. Correcting for dust requires assumptions about the dust distribution and properties, adding another layer of uncertainty. Furthermore, the line and alpha line, one of the strongest lines from hydrogen, is easily absorbed by neutral hydrogen along the line of sight, both within the galaxy and in the intergalactic medium, and at high redshifts during the epoch of reionization, when the intergalactic medium was still partly neutral, Lyman alpha emission can be heavily suppressed, making the line weak or undetectable, even in a vigorously star-forming galaxy. Spectroscopy with Webb's NIRSpec instrument has been crucial for confirming the redshifts of these candidate high-redshift galaxies and for studying their properties. Photometric redshifts, based on broadband filter imaging, can be ambiguous. A galaxy's colors can be consistent with more than one redshift, especially if the galaxy is dusty or has unusual stellar populations. Obtaining a spectrum resolves this ambiguity by revealing the detailed features absorption and emission lines that are unique to specific elements and ionization states, and that shift in wavelength according to the redshift. The detection of multiple lines at consistent redshifts provides a robust measurement, and the line strengths and profiles provide physical information. Several of the Webb high redshift candidates have been followed up spectroscopically, and in many cases the photometric redshifts have been confirmed, with spectroscopic redshifts of Z greater than 10, 11, or even 13 measured through lines such as the Lyman alpha line, though this is often weak or absent, the Lyman beta line, and metal lines from oxygen, carbon, and nitrogen. The spectra reveal actively star-forming galaxies with emission lines indicating ionization by young hot stars, consistent with ongoing star formation. The line ratios can be used to estimate the metallicity. And interestingly, some of these galaxies show metallicities that, while low compared to local galaxies, are not zero, suggesting that chemical enrichment has already occurred, that supernovae have exploded and produced heavy elements, and that the gas has been mixed to some extent. This chemical enrichment requires time, reinforcing the puzzle of how these galaxies became so evolved so quickly. In some cases, the spectra also show broad emission lines characteristic of an active galactic nucleus, or AGN, indicating the presence of a supermassive black hole at the galaxy's center, accreting gas and emitting intense radiation. The detection of AGN at such high redshifts is itself surprising because supermassive black holes are thought to grow from smaller seed black holes, which themselves must form from the collapse of massive stars or gas clouds, and then grow through accretion and mergers. Growing a black hole from a stellar mass seed of a few tens of solar masses to a supermassive black hole of millions or billions of solar masses takes time. Limited by the Eddington limit, the maximum rate at which a black hole can accrete without the radiation pressure from the accretion disk blowing away the infalling gas. Even under optimal conditions, growing a billion solar mass black hole from a stellar seed requires continuous accretion at the Eddington limit for hundreds of millions of years. And detecting such objects at Z equals 13 only 300 million years after the Big Bang suggests either that the seeds were much larger than expected, perhaps forming from the direct collapse of massive gas clouds into black holes of thousands or tens of thousands of solar masses, or that the black holes grew faster than the Eddington limit, perhaps through super-Eddington accretion phases. The presence of active galactic nuclei complicates the interpretation of the galaxy properties because the AGN emission can contribute significantly to the total light, especially at certain wavelengths, and can dominate the emission lines, masking the signatures of star formation. Separating the AGN contribution from the stellar contribution requires careful modeling, and in some cases it is possible that some of the luminosity attributed to stars is actually coming from the AGN, which would mean the stellar masses have been overestimated. However, in many of the high redshift galaxies, the SEDs and spectra are consistent with star formation being the dominant source of light, with little or no contribution from an AGN, so this does not appear to be a universal explanation for the high luminosities. Gravitational lensing has been a valuable tool for studying these distant galaxies. When a massive foreground object, such as a galaxy cluster, lies along the line of sight to a more distant galaxy, the gravity of the foreground mass bends and magnifies the light from the background galaxy, effectively creating a natural telescope. The magnification can be factors of 10, 20, or even more, allowing much fainter galaxies to be detected and studied in detail. Webb has observed several lensing clusters, and the lensed high redshift galaxies provide some of the best data on the early universe. The lensing magnification also allows the spatial structure of the galaxies to be resolved, revealing that some of these early galaxies are quite compact, with sizes of only a few hundred parsecs, much smaller than modern galaxies, though this compactness is consistent with models of early galaxy formation, where gas collapses into dense clumps. However, lensing introduces its own complexities. The magnification is not uniform across the galaxy and depends on the detailed mass distribution of the lensing cluster, which must be modeled using the positions and distortions of multiple lensed images. Errors in the lensing model translate into errors in the inferred magnification, and thus in the intrinsic properties of the lens galaxy. In some cases, the magnification can be very high, and small errors in the model can lead to large uncertainties in the intrinsic luminosity and stellar mass. This means that while lensed galaxies provide valuable information, their properties must be interpreted with care, and independent checks with unlensed galaxies are important. The statistical significance of the excess of bright galaxies at high redshift is also a subject of active investigation. Early papers reported candidate galaxies with redshifts up to Z equals 16 or even higher, with luminosities that would make them extraordinarily bright for their epoch. But as more data have been obtained and more careful analyses performed, some of these candidates have been found to be at lower redshifts, with their high redshift photometric estimates the result of unusual colors or contamination. Spectroscopy has been essential for confirming or refuting these candidates, and the confirmed population at Z greater than 10 is smaller than the initial photometric samples, though still larger than standard models predicted. The question is whether the number of bright galaxies at these redshifts is marginally higher than expected, which might be accommodated by tweaking model parameters within reasonable ranges, or whether the excess is so large that it requires fundamentally new physics or astrophysics. Some analyses suggest that the excess is statistically significant at several sigma, meaning it is unlikely to be a random fluctuation, but the exact significance depends on how one defines the sample, what luminosity or stellar mass threshold one uses, how one accounts for incompleteness and selection effects, and what theoretical predictions one compares to. Different groups have reached somewhat different conclusions, with some arguing that the tension with lambda CDM is severe and requires new physics, while others suggest that the observations can be explained within the standard model if one adopts more optimistic assumptions about star formation efficiency, the initial mass function, or feedback processes. This is an area of ongoing research and debate, with new data from Webb and refined models likely to clarify the situation over the coming years. One proposed solution to the early galaxy problem is to increase the efficiency of star formation in the early universe. In standard models, the efficiency with which gas is converted into stars is relatively low because feedback processes, such as supernova explosions and stellar winds, inject energy into the gas, heating it, and driving outflows that remove gas from the galaxy or prevent it from cooling and forming stars. If the feedback is less efficient in the early universe, perhaps because the galaxies are deeper in their gravitational potential wells, or because the gas is distributed differently, then a higher fraction of the available gas could form stars, leading to more rapid buildup of stellar mass. Some models invoke reduced feedback by assuming that supernovae are less efficient at coupling their energy to the gas, or that the gas is more clumpy, so that feedback energy escapes without affecting all the gas, allowing some regions to continue forming stars undisturbed. Another possibility is that the initial mass function was different in the early universe. The IMF describes the distribution of stellar masses formed in a burst of star formation, typically assumed to follow a salpeter or Krupa distribution, which is skewed toward low-mass stars, with many more stars of 1 solar mass, or less than stars of 10 or 100 solar masses. However, the IMF is thought to depend on the properties of the gas, such as its temperature, density, and metallicity, and in the metallicity and in the metal-free gas of the first generation of stars. The IMF might have been top-heavy, favoring the formation of very massive stars. If the IMF remains somewhat top-heavy, even after the first generation, with a higher proportion of massive stars than in modern galaxies, then the light per unit stellar mass would be higher, and the galaxy would appear more luminous, potentially reconciling the high luminosities with the available time for star formation. A top-heavy IMF would also affect the chemical enrichment history, producing more heavy elements per unit stellar mass, and the feedback, since massive stars produce more energetic explosions. The role of dark matter in setting the pace of galaxy formation is also being re-examined. The lambda CDM model assumes that dark matter is cold, meaning it has negligible thermal velocities, and that it interacts only through gravity. These assumptions lead to a specific prediction for the growth of structure, with the smallest halos forming first. However, if dark matter has different properties, such as being warm, with higher thermal velocities, or if it has weak interactions with ordinary matter or with itself, the formation of structure could be different. Warm dark matter, for example, suppresses the formation of the smallest halos because the thermal velocities smooth out fluctuations on small scales, but it does not significantly affect larger scales, so it would not necessarily change the timeline for forming galaxies at the masses Webb is observing. Other dark matter models, such as self-interacting dark matter, can affect the inner density profiles of halos, but again, the impact on the timing of galaxy formation is not straightforward. Some researchers have suggested that the cosmological parameters themselves might need revision. The lambda CDM model has a set of parameters that describe the universe's composition and evolution, such as the Hubble constant, which sets the expansion rate, the matter density, and the amplitude of the initial fluctuations. These parameters have been measured with high precision using the cosmic microwave background, large-scale structure surveys, and other probes. And the different measurements are generally consistent, forming a coherent standard cosmology. However, there are some tensions in the data, most notably the so-called Hubble tension, where measurements of the Hubble constant from the cosmic microwave background give a value around 67 kilometers per second per megaparsec, while measurements from local distance indicators give a value around 73, a discrepancy that is statistically significant and not easily explained. If the true value of the Hubble constant is higher, the universe would be younger, leaving even less time for galaxies to form, which would worsen the problem. But if some other parameter, such as the amplitude of fluctuations, is different, it could affect the formation timeline in a way that might help. Another direction being explored is the possibility of very efficient early black hole formation and growth. If supermassive black holes form early and grow rapidly, they can influence the surrounding gas through feedback, but they can also in some circumstances help trigger star formation by compressing gas or by providing a source of energy that heats and ionizes the gas in a way that actually facilitates subsequent cooling and collapse. The interplay between black hole growth and star formation is complex, and it is possible that in the early universe, this interplay operated differently, leading to a burst of star formation earlier than standard models predict. The detection of AGN at high redshift supports the idea that black holes were growing early, and if this growth was widespread, it might have affected the broader galaxy population. The clustering of high redshift galaxies, their spatial distribution on the sky, provides another observational constraint. If galaxies are forming in the densest regions, as expected in hierarchical models, they should be clustered together. And the strength of the clustering depends on the bias, the relationship between the distribution of galaxies and the underlying dark matter distribution. Measuring the clustering of high redshift galaxies can test models of structure formation and provide information about the mass of the dark matter halos hosting these galaxies. Early analyses of Webb data suggest that the high redshift galaxies are indeed clustered, but the strength of the clustering and its implications for halo masses are still being worked out. Cosmic variance, the statistical fluctuation in the number of galaxies due to the finite size of the observed volume, is also a consideration. Webb's deep surveys cover relatively small areas of the sky, and the number of high redshift galaxies detected in any given field can fluctuate significantly due to large-scale structure, overdensities or underdensities in the galaxy distribution. If Webb happens to be observing a particularly overdense region at high redshift, it could detect more galaxies than average, giving the impression of an excess. However, as more fields are observed and the total survey area increases, cosmic variance should average out, and the true space density of high redshift galaxies will become clearer. Some of the early surprises might be due to observing lucky fields. But the fact that multiple independent surveys have found bright high redshift galaxies suggests that the effect is not purely due to cosmic variance. The dust properties in the early universe remain uncertain. Dust is produced by stars primarily through the winds of evolved stars on the asymptotic giant branch and through supernova explosions, and the composition and properties of dust depend on the elements available, which in turn depend on the history of nucleosynthesis. In a low metallicity environment, there are fewer heavy elements to form dust, and the dust that does form might have different properties, different grain sizes or compositions, affecting how it absorbs and emits light. Observations of dust in high redshift galaxies, through infrared emission detected by Webb's MIRI instrument, or through submillimeter observations with ground-based telescopes, can constrain the dust mass and properties, but interpreting these observations requires models of dust formation, destruction, and evolution, which are themselves uncertain. The role of gas inflows and outflows is another key factor. Galaxies do not form in isolation. They are part of the cosmic web, and gas can flow into galaxies along filaments, feeding star formation, while outflows driven by supernovae, stellar winds, or AGN feedback can expel gas, quenching star formation. The balance between inflows and outflows determines the gas supply available for star formation, and thus the rate at which stellar mass builds up. In the early universe, the gas inflow rates are expected to be high because galaxies are still assembling and the surrounding intergalactic medium is dense and relatively cool. But if feedback-driven outflows are also strong, they can regulate the star formation and prevent runaway growth. Simulations of galaxy formation attempt to model these processes, but they are challenging because the physics operates on a wide range of scales, from the large-scale flows of gas through the cosmic web down to the small-scale processes in individual star-forming regions and supernova remnants. The ionizing photon budget of the early universe is intimately connected to galaxy formation. Reionization, The process by which the intergalactic medium was ionized by the first stars and galaxies requires a sufficient number of ionizing photons, photons with energies above 13.6 electron volts, capable of ionizing hydrogen. The production rate of these photons depends on the number and properties of star-forming galaxies, including their star formation rates and the escape fraction, the fraction of ionizing photons that escape from the galaxy into the intergalactic medium, rather than being absorbed by gas and dust within the galaxy. If galaxies at high redshift are more numerous and more luminous than expected, they could produce more ionizing photons, potentially reionizing the universe earlier or more rapidly than standard models predict. Conversely, constraints on the reionization history from observations of the cosmic microwave background and quasar absorption spectra can be used to place limits on the properties of high redshift galaxies. The timing and topology of reionization are inferred from several lines of evidence. The cosmic microwave background polarization is sensitive to the integrated optical depth, to Thomson scattering by free electrons, which depends on when reionization occurred. Earlier reionization means more free electrons along the line of sight and higher optical depth. The Planck satellite measured the optical depth and found a value consistent with reionization, being largely complete by around z equals 6 to 8, with some earlier contribution, but the data do not pin down the exact history. Observations of distant quasars show absorption features from neutral hydrogen along the line of sight, and the evolution of these absorption features, with redshift traces the ionization state of the intergalactic medium. Complete absorption. A Gunn-Pedersen trough is seen at redshifts above about 6, indicating significant neutral hydrogen, while at lower redshifts, the intergalactic medium is highly ionized. The transition suggests that reionization was largely complete by around z equals 6, roughly 1 billion years after the Big Bang, but the exact timeline and whether reionization proceeded uniformly or in a patchy manner are still open questions. If the high redshift galaxies Webb is finding are representative of the broader population, their contribution to reionization would need to be included in models, and their high luminosities and implied high star formation rates would boost the ionizing photon production. However, the escape fraction of ionizing photons is a critical uncertainty. In local star-forming galaxies, escape fractions are typically very low, only a few percent, because the ionizing photons are absorbed by surrounding gas and dust. In high redshift galaxies, the escape fraction might be higher if the galaxies are less dusty, or if the gas distribution is clumpy, with channels through which photons can escape. Some studies suggest escape fractions of 10 to 30% for high redshift galaxies, and if the Webb galaxies have high escape fractions, they could be major contributors to reionization. On the other hand, if their escape fractions are low, their contribution would be modest despite their high luminosities, and other sources, such as faint, low-mass galaxies below Webb's detection threshold, might dominate the ionizing photon budget. The connection between the first stars and the first galaxies is another layer of the story. The very first stars, population 3 stars, formed in many halos of dark matter, in regions where gas could cool and collapse, but where no heavy elements were yet present. These stars were likely very massive, perhaps 100 to 300 solar masses, and they lived for only a few million years before exploding as parent stability supernovae or collapsing directly into black holes. The remnants of these first stars, the heavy elements they produced and the black holes they left behind, would have seeded the next generation of star formation. Population 2 stars, formed from gas enriched by the first supernovae, would have a broader range of masses, more like modern stars, and they would begin to build up the stellar populations of the first galaxies. The transition from population 3 to population 2 star formation marks the beginning of true galaxy formation, and the timescale for this transition is uncertain, but it is thought to occur over a few tens of millions of years, depending on how quickly the first supernovae mix their products into the surrounding gas, and how quickly new regions collapse and form stars. Webb's observations do not directly detect population 3 stars because these stars are individually too faint and too short-lived, and the signal from a single such star would be overwhelmed by the light from the surrounding galaxy. However, the properties of the earliest galaxies, their chemical compositions and stellar populations, can provide indirect evidence of the first stars. If a galaxy shows very low metallicity, close to zero, it might be in the process of forming its first stars, while if it shows significant metallicity, it has already undergone multiple generations of star formation. The spectra of some high redshift galaxies observed by Webb show emission lines from elements like oxygen and carbon, indicating that nucleosynthesis has occurred. But the metallitilities are still being measured, and the uncertainties are large because the line strengths depend on many factors, including the ionization state, the density, and the dust. The spatial distribution of star formation within high redshift galaxies is also of interest. Are these galaxies forming stars in a centrally concentrated manner, building up a dense core, or is star formation distributed throughout the galaxy, or even occurring in multiple distinct clumps that might later merge? Imaging with Webb can resolve the spatial structure of nearby high redshift galaxies, especially those that are gravitationally lensed and thus magnified, and the images reveal a variety of morphologies, some galaxies appearing compact and smooth, others showing clumpy or irregular structure. This diversity suggests that galaxy formation proceeds through different pathways, with some systems building up smoothly through continuous gas accretion and star formation, while others grow through mergers of smaller clumps, a process sometimes called clumpy accretion. The theoretical framework for understanding these observations draws on simulations that model the formation and evolution of galaxies from first principles. The simulations start with initial conditions set by the cosmic microwave background representing the density fluctuations at recombination, and evolve the dark matter and gas forward in time under gravity, hydrodynamics, and various physical processes such as cooling, star formation, and feedback. The most sophisticated simulations, such as the Illustris, Gelli, and Simba projects, use large computational boxes and high resolution to capture both the large-scale structure and the detailed processes within individual galaxies. These simulations have been successful in reproducing many observed properties of galaxies in the local universe, such as the galaxy's stellar mass function, the star formation rate as a function of mass, and the morphologies and colors of galaxies. However, simulations rely on subgrid models to handle processes that occur on scales smaller than the resolution, such as star formation within molecular clouds and supernova explosions. These subgrid models contain free parameters that are calibrated by matching the simulations to observations, and the calibration is typically done using data from the local universe or at modest redshifts, z less than 3 or so, where observations are more complete. Extrapolating these models to z greater than 10 into a regime where they have not been calibrated introduces uncertainty, and it is possible that the subgrid parameters need to be adjusted to match the high redshift observations, or that new physical processes, not included in the current models, become important at early times. Some simulations specifically designed to study the high redshift universe, such as the Renaissance simulations and First Light, have focused on the first galaxies, using very high resolution and small volumes to capture the formation of mini-hollows in the first stars. These simulations predict a population of small, faint galaxies at high redshift, in broad agreement with the hierarchical formation picture, but they also show that the properties of individual galaxies can vary widely depending on their assembly history, the timing of star formation, and the impact of feedback. The simulations generally predicted that massive galaxies are rare at very high redshifts, and the number of galaxies with stellar masses greater than 1 billion solar masses at z greater than 10 is very small, on the order of a few per cubic gigaparsec or less, whereas the Webb observations suggest a higher number density. One approach to reconciling the observations with simulations is to run new simulations with updated physics or different parameter choices. And several groups are doing this, exploring how changes to the star formation efficiency, the feedback prescriptions, or the initial mass function affect the high redshift galaxy population. Preliminary results suggest that increasing the star formation efficiency or reducing the feedback can produce more massive galaxies at high redshift, but the parameter changes required are often large, pushing the models away from the values that match observations at lower redshifts, which raises questions about whether a single set of parameters can fit the data across all epochs, or whether the physics of galaxy formation evolves with redshift in a way not captured by current models. Another approach is to invoke exotic physics or astrophysics that is not part of the standard model. For example, if there were a phase of very rapid structure formation, perhaps associated with a period of enhanced dark matter clustering, or a spike in the primordial power spectrum at certain scales, more structure could form early, seeding earlier galaxy formation. Primordial black holes, hypothetical black holes formed in the very early universe, could serve as seeds for supermassive black holes, and could affect the surrounding matter, though their existence and properties are highly speculative. Modified gravity theories, which alter the law of gravity on cosmological scales, could change the growth rate of structure, but most such theories are tightly constrained by observations of the cosmic microwave background and large-scale structure, leaving little room for significant deviations that would affect early galaxy formation. The role of baryonic physics, the behavior of ordinary matter as opposed to dark matter, is perhaps the most promising area for finding solutions. Dark matter provides the gravitational scaffolding, but the stars we observe are made of baryons, and the conversion of gas into stars is a complex astrophysical process with many feedback loops. Small changes in how this process operates, changes that might be justified by different conditions in the early universe, could have large effects on the resulting galaxy properties. For instance, If the cooling of gas was more efficient in the early universe, perhaps because the gas was more pristine, or because the radiation field was different, gas could collapse more rapidly, leading to faster star formation. Or if the magnetic fields in the early universe were weaker, reducing the support against collapse, gas could again collapse more easily. The magnetic fields in galaxies are thought to be amplified from weak seed fields by dynamo processes associated with turbulence and differential rotation, and this amplification takes time, so the first galaxies might have had much weaker magnetic fields than modern galaxies. Magnetic fields provide pressure support and can affect the fragmentation of gas clouds, influencing the star formation rate and the initial mass function. Weaker fields might allow more rapid fragmentation and higher star formation rates, though the details depend on the complex interplay between gravity, pressure, and magnetic tension. Observing magnetic fields in high redshift galaxies is challenging because the standard method, using the polarization of synchrotron emission or the Faraday rotation of polarized light, requires detecting faint radio emission, which is difficult at such distances, but future radio telescopes such as the Square Kilometre Array may be able to probe this. The chemical evolution of galaxies, the buildup of heavy elements over time, is closely tied to the star formation history, because stars produce heavy elements and return them to the interstellar medium through winds and explosions. The metallicity of a galaxy at a given time reflects its integrated star formation history and the efficiency of mixing and retention of heavy elements. In the standard picture, the first galaxies start with zero metallicity, and as they form stars, supernovae enrich the gas, gradually increasing the metallicity over time. The rate of enrichment depends on the star formation rate, the yield of heavy elements from supernovae, which itself depends on the initial mass function and the stellar masses, and the fraction of gas that is lost through outflows versus retained in the galaxy. If a galaxy at Z equals 13 shows a metallicity of, say, 10% of solar, this implies that a significant amount of star formation has already occurred, producing supernovae that made the heavy elements, and that the gas has been mixed so that the products are distributed throughout the star-forming regions. The time required for this chemical evolution depends on the star formation rate and the supernova rate, but it is typically on the order of tens of millions of years, comparable to the lifetimes of massive stars. Detecting such metallicities at very high redshifts thus implies that star formation began quite early, perhaps within the first 100 million years after the Big Bang, and proceeded vigorously. Some models suggest that the first galaxies could enrich quickly through very intense starbursts, producing many supernovae in a short time, and if the gas is well mixed by turbulence, the metallicity could rise rapidly. The turbulence in high redshift galaxies is expected to be high because of the vigorous star formation and feedback, and also because of the infall of gas from the surrounding intergalactic medium, which can shock, heat, and stir the gas as it accretes onto the galaxy. Turbulence affects many aspects of galaxy evolution, from the mixing of chemicals to the transport of angular momentum, which influences the formation of disks and other structures. High turbulence can support the gas against collapse, slowing star formation, but it can also drive gas inflows toward the center, feeding star formation and black hole growth. The balance between these effects depends on the scale and properties of the turbulence, which in turn depend on the sources of energy injection, primarily supernovae and stellar winds, and on the dissipation mechanisms, such as shocks and radiative cooling. The angular momentum of gas is another important factor. As gas collapses under gravity, conservation of angular momentum causes it to spin up. And if the angular momentum is high, the gas can form a rotating disk rather than collapsing directly to a central point. The formation of disks is thought to be a key step in the evolution of galaxies, leading to the spiral galaxies we see in the local universe. But the process is not straightforward because feedback can remove or redistribute angular momentum, and mergers can disrupt disks. In the very early universe, it is unclear how much angular momentum the collapsing gas has and how efficiently disks form. Some of the high redshift galaxies observed by Webb appear compact and centrally concentrated, suggesting that they have not yet formed large rotating disks, while others show more extended and complex structures that might be disk-like or might be the result of mergers. The merger history of high redshift galaxies is another aspect being investigated. Mergers are a fundamental part of hierarchical structure formation, and in the early universe, the merger rate should be high because galaxies are closer together in physical space, and because the overall density of the universe is higher. Mergers can trigger starbursts by driving gas into the center of the merging system, and they can also lead to the rapid buildup of stellar mass. If the high redshift galaxies observed by Webb are the products of recent mergers, this could help explain their high stellar masses, as mergers effectively combine the stellar populations of the progenitor galaxies. However, mergers also disturb the structure of galaxies, creating irregular morphologies and possibly triggering AGN activity. so observing the morphology and kinematics of these galaxies can provide clues about their recent history. Kinematics, the study of the motions of gas and stars within galaxies, is accessible through spectroscopy by measuring the Doppler shifts and line widths of emission and absorption lines. A galaxy with ordered rotation will show a smooth velocity gradient across its extent, with one side approaching and the other receding, while a galaxy with chaotic or turbulent motions will show broad lines and irregular velocity patterns. Observing the kinematics of high redshift galaxies is challenging because they are faint and often compact, requiring high spatial and spectral resolution, but Webb's NIRSpec instrument can obtain spatially resolved spectra, and early results are beginning to reveal the internal dynamics of some high redshift systems, showing evidence of both rotation and turbulence. The star formation histories of individual galaxies, the detailed record of how their star formation rates have varied over time, can be inferred from their spectral energy distributions by comparing the observed SEDs to models that incorporate different star formation histories, such as constant star formation, exponentially declining star formation, or bursts of star formation. The inferred star formation histories provide insights into whether a galaxy has been forming stars steadily or has undergone episodes of intense activity. For the high redshift galaxies with very high stellar masses, the inferred star formation histories often require very high star formation rates sustained over most of the available time, approaching or even exceeding the Eddington limit for star formation, a theoretical upper limit based on the idea that radiation pressure from stars can unbind the gas if the star formation rate is too high. The Eddington limit for star formation is not a hard physical boundary but a rough guide, and it can be exceeded in certain circumstances, such as if the gas is very dense and self-shielding, preventing radiation from escaping and exerting pressure, or if the star formation is concentrated in a small region where the gravitational forces are very strong. Some models of high redshift galaxies invoke super-Eddington star formation to explain the rapid buildup of stellar mass, but sustaining such extreme conditions for long periods is difficult, and it is unclear whether the necessary conditions existed in the early universe. Observational tests, such as measuring the star formation rates through emission lines or infrared luminosity and comparing them to the stellar masses and ages, can help constrain the star formation histories and test these models. The infrared luminosity of a galaxy, particularly in the mid and far infrared, is a tracer of star formation because young stars heat dust, which then emits in the infrared. The total infrared luminosity can be integrated to estimate the star formation rate using a conversion factor derived from stellar population models, and this infrared-based star formation rate can be compared to estimates from ultraviolet luminosity or emission lines to check for consistency and to assess the impact of dust. For high redshift galaxies, the observed mid-infrared emission, detected by Webb's MIRI instrument, corresponds to rest frame wavelengths in the near to mid-infrared, probing the emission from warm dust heated by star formation, and the brightness at these wavelengths can be used to estimate the dust mass and the obscured star formation rate. Some of the high redshift galaxies detected by Webb show significant mid-infrared emission, indicating the presence of warm dust, which in turn suggests either substantial star formation or, in some cases, an active galactic nucleus. Distinguishing between these scenarios requires detailed SED fitting and spectroscopy, but the presence of dust at such early times is itself noteworthy because, as mentioned earlier, dust must be produced by stars and supernovae, and rapid dust production requires efficient star formation and supernovae. The dust composition and properties can also be probed through the shape of the infrared SED, as different dust grains have different emissivity curves, but the uncertainties are large, and more data are needed to draw firm conclusions. The far infrared and sub-millimeter emission, corresponding to emission from cooler dust, has been observed for a handful of high redshift galaxies using ground-based sub-millimeter telescopes such as ALMA, the Atacama Large Millimeter/Sub-Millimeter Array. ALMA has detected dust continuum emission and molecular line emission, such as from carbon monoxide and ionized carbon, in some of the most distant galaxies known, providing measurements of the gas and dust masses and the kinematics. These observations complement Webb's infrared data, and together they build a more complete picture of the gas, dust, and star formation in early galaxies. The ALMA observations confirm that some high redshift galaxies have large reservoirs of molecular gas, the fuel for star formation, and that the gas is dynamically complex, sometimes showing signs of rotation, other times showing more disturbed kinematics indicative of mergers or inflows. The fraction of gas in galaxies, the gas fraction, is the ratio of gas mass to total baryonic mass, and it is expected to be high in the early universe because star formation has not yet converted much of the gas into stars. Observations of high redshift galaxies indeed suggest high gas fractions, often 50% or more, compared to 10 to 20% in local galaxies, consistent with the idea that early galaxies are gas-rich and rapidly forming stars. The high gas fractions also imply that the galaxies have substantial reservoirs to sustain star formation, potentially for hundreds of millions of years if the star formation rates remain high, though feedback and outflows can deplete the gas over time, eventually quenching star formation. Quenching, the cessation of star formation, is an important process in galaxy evolution, leading to the formation of passive, red galaxies that dominate the massive galaxy population in the local universe. Quenching can occur through several mechanisms, including the exhaustion of the gas supply, the ejection of gas by feedback, the prevention of gas inflows by a hot gaseous halo, or the stripping of gas by interactions with other galaxies or the intergalactic medium. In the early universe, quenching is expected to be less common because the gas supply is abundant and the feedback, while energetic, has to work against strong gravitational forces and continuous gas inflows. However, if some high redshift galaxies have very intense feedback, perhaps from an AGN or from an extreme starburst, they could be quenched early, becoming passive systems at high redshift. Detecting such passive galaxies at Z greater than 10 would be surprising and would challenge models further. But so far, most of the high redshift galaxies observed by Webb appear to be actively star-forming. The colors of galaxies provide a simple diagnostic of their stellar populations. Star-forming galaxies tend to be blue because they have young, hot stars emitting strongly in the ultraviolet, while passive galaxies are red because they are dominated by older, cooler stars. At high redshifts, the observed colors are shifted into the infrared, but the same principle applies. Some of the high redshift candidates initially identified by their red colors turned out to be dusty star-forming galaxies rather than passive systems, because dust reddens the light, making the galaxy appear red even though it is actively forming stars. Distinguishing between dust reddening and age-related reddening requires detailed SED modeling or spectroscopy to measure the strength of the Balmer break or other features that are sensitive to stellar age. The Balmer break is a feature in the spectrum of a galaxy caused by the absorption of photons by hydrogen in the atmospheres of stars, occurring at a wavelength of about 365 nanometers in the rest frame, corresponding to the ionization edge of hydrogen in the n=2 energy level. In a young stellar population dominated by hot stars, the Balmer break is weak, while in an older population dominated by cooler stars, the break is strong, creating a sharp drop in the flux at wavelengths shorter than the break. Observing the Balmer break at high redshift requires infrared observations because the feature is redshifted into the near-infrared. And Webb's sensitivity and wavelength coverage make it possible to detect and measure the break for high redshift galaxies, providing constraints on the ages of their stellar populations. The ages derived from SED fitting for the high redshift galaxies with large stellar masses are often surprisingly old, in some cases a few 100 million years, which, given the age of the universe at the time, implies that star formation began very early, possibly as early as 100 million years after the Big Bang, or even earlier. This pushes back the epoch of the first stars and the first galaxies, and if confirmed, it means that the processes leading to star formation, the cooling and collapse of gas, the formation of molecular clouds, and the ignition of fusion, all proceeded very rapidly after the Big Bang, leaving little time for the dark ages to unfold as traditionally envisioned. The formation of molecular hydrogen, H2, is a critical step in the cooling of primordial gas, because molecular hydrogen is the primary coolant in metal-free gas, radiating away energy through rotational and vibrational transitions and allowing the gas to cool below about 10,000 Kelvin, the temperature below which atomic cooling is ineffective. Without H2, gas in mini-hollows would remain too hot to collapse to the densities needed for star formation. The formation of H2 occurs through chemical reactions on the surfaces of dust grains, or, in the absence of dust, through gas phase reactions involving free electrons and protons forming negatively charged hydrogen ions, H-, which then combine with neutral hydrogen to form H2. The gas phase route is slow and inefficient, and the formation of sufficient H2 to cool the gas takes time, typically millions of years, which sets a lower limit on the timescale for the first star formation. However, if conditions in the early universe were different, perhaps with higher densities or different radiation fields, the H2 formation rate could have been enhanced, speeding up the cooling and collapse. Some models suggest that the first stars could have formed as early as 30 to 50 million years after the Big Bang in the densest regions, though this is at the extreme end of predictions. If such early star formation occurred, the galaxies we see at Z=13 or higher could be the descendants of these very early systems, having accumulated several generations of stars over 200 to 300 million years. Alternatively, if star formation began more typically around 150 to 200 million years, the high redshift galaxies would represent the first generation of true galaxies. and their high stellar masses would require extremely efficient star formation over the available time. The gravitational potential wells of dark matter halos play a central role in determining which halos can form stars and when. The minimum mass for a halo to cool and form stars, the so-called cooling mass, depends on the cooling mechanisms available. Before reionization, when the intergalactic medium is neutral, gas can cool through atomic hydrogen and H2, and the cooling mass is relatively low, around 1 million solar masses for mini-halos, forming the first stars. After reionization, the intergalactic medium is ionized and heated to tens of thousands of Kelvin by the ionizing radiation from stars and quasars, and this raises the cooling mass because gas in small halos is photoheated by the ionizing background, preventing it from cooling and collapsing. The new cooling mass threshold, often called the filtering mass, is around 10 to the 8th or 10 to the 9th solar masses, meaning that only halos more massive than this can cool and form stars after reionization. The timing of reionization thus affects the assembly of galaxies because it suppresses star formation in small halos. If reionization occurs early at Z greater than 10 or 15, it would cut off star formation in low-mass halos and shift galaxy formation to more massive systems, potentially leading to fewer but more massive galaxies forming in the early universe, which might help explain the Webb observations. However, as mentioned earlier, current constraints suggest reionization was largely complete by Z around 6 to 8. Not much earlier, so while reionization certainly affected galaxy formation, it is not clear that it occurred early enough to have a major impact on the galaxies observed at Z greater than 10. Moreover, the most massive galaxies observed by Webb are likely to be forming in halos above the filtering mass anyway, so photoheating might not have been a major obstacle for them. The environment in which galaxies form, the surrounding density field, and the presence of nearby halos can influence their properties. Galaxies forming in overdense regions, in the peaks of the density distribution, are expected to form earlier and to merge more frequently, building up mass more rapidly than galaxies in average or underdense regions. The highest redshift galaxies should preferentially be found in such overdense regions, and indeed some studies suggest that the high redshift galaxies detected by Webb are more clustered than expected, indicating they are in overdense environments. This clustering could mean that the observed galaxies are not typical but are the rare early forming systems in the densest peaks, and that the overall galaxy population at these redshifts is lower in number but includes these exceptional systems. This would ease the tension with models because the models also predict rare massive galaxies in the highest density peaks, though the number and properties of these galaxies would still need to match observations. Cosmic reionization and the formation of the first galaxies are intimately linked, and understanding one requires understanding the other. The sources of reionization are thought to be primarily stars in the first galaxies, though quasars and other exotic sources could also contribute. The efficiency of reionization depends on the total ionizing photon output from all galaxies, integrated over the population, and on the clumpiness of the intergalactic medium, which affects how efficiently the ionizing photons propagate and ionize hydrogen. If the galaxy population at high redshift is more luminous or more numerous than standard models predict, the ionizing photon budget could be larger, reionizing the universe faster or earlier. Conversely, if the escape fraction of ionizing photons is lower, the contribution per galaxy is reduced, and more galaxies are needed to achieve reionization. The topology of reionization, whether it proceeds inside out with ionized bubbles growing around the densest regions where galaxies form first, or outside in, or in a more complex patchy manner, depends on the spatial distribution of the ionizing sources and the inhomogeneity of the intergalactic medium. Observations of the Lyman alpha forest, the absorption of quasar light by neutral hydrogen at multiple redshifts along the line of sight, provide information about the ionization state as a function of redshift and position. And these observations can be compared to simulations of reionization that model the growth and overlap of ionized regions. The simulations depend on the properties of the galaxy population, so the Webb observations can be fed into reionization models to test whether the observed galaxies produce the right ionizing photon budget and the right reionization history. Early results from such efforts suggest that if the high redshift galaxies observed by Webb are typical, and if their escape fractions are not too low, they could contribute significantly to reionization, potentially dominating the ionizing photon budget at Z greater than 8 or 10. This would represent a shift from the previous picture where faint, low-mass galaxies below the detection threshold of Hubble and only marginally accessible to Webb were thought to dominate reionization. However, the uncertainties in the escape fraction and in the completeness of the Webb surveys mean that this conclusion is still tentative, and more work is needed to determine the relative contributions of different galaxy populations to reionization. The stellar populations themselves, the mix of stars of different masses, ages, and metallicalities encode the history of a galaxy. Observations of stellar populations in the local universe, where individual stars can be resolved and studied in detail, provide benchmarks for understanding how stars form and evolve, and these benchmarks are used to construct stellar population synthesis models, which predict the integrated light from a population of stars as a function of age, metallicity, and star formation history. These models are then applied to high-redshift galaxies, where individual stars cannot be resolved, and the total light from millions or billions of stars is observed together. By fitting models to the observed SEDs, astronomers infer the stellar population properties, but the process is fraught with degeneracies, as different combinations of age, metallicity, and dust can produce similar SEDs. Breaking the degeneracies requires additional constraints such as spectroscopy to measure specific features that are sensitive to particular properties, or resolved observations to study spatial variations within the galaxy. For the high-redshift galaxies observed by Webb, obtaining such detailed data is pushing the limits of current capabilities, but the quality of Webb's data is unprecedented, and careful analysis is revealing features that were not accessible before. For example, the detection of the Balmer break in some high-redshift galaxies provides a strong constraint on age, while the detection of emission lines provides constraints on the ionization state and the star formation rate. Combining these constraints improves the accuracy of the inferred stellar masses and ages, though significant uncertainties remain. The initial mass function, mentioned earlier, is one of the fundamental uncertain parameters in stellar population models. The IMF determines how mass is distributed among stars, and it affects both the light output per unit stellar mass and the chemical yield per unit star formation. If the IMF is universal, the same in all galaxies and at all times, then models calibrated in the local universe can be applied at high redshift with confidence. But if the IMF varies, especially in the early universe where conditions were very different, then extrapolating local models to high redshift introduces errors. Theoretical arguments suggest that the IMF could depend on the properties of the gas, such as temperature, pressure, and metallicity, and in the metal-free gas of the first stars, the IMF was likely very different, skewed toward massive stars. As metallicity increased with successive generations of stars, the IMF might have transitioned toward the form observed locally, but the redshift at which this transition occurred is unknown. Observationally testing the IMF at high redshift is difficult because it requires measuring both the light output and the stellar mass independently, or measuring features that are sensitive to the relative numbers of stars of different masses, such as the ratio of ultraviolet to infrared luminosity or the strength of certain absorption features in the spectrum. Some studies of high redshift galaxies have suggested that the IMF might be top-heavy, based on the high ultraviolet luminosities relative to the inferred stellar masses, but the evidence is not yet conclusive, and alternative explanations, such as very young ages or bursty star formation, can produce similar effects. More work is needed to pin down the IMF at high redshift and Webb's spectroscopic capabilities. Allowing the measurement of detailed line ratios and spectral features will be instrumental in this effort. The bursty nature of star formation in small high redshift galaxies is another complication. Instead of forming stars at a steady rate, small galaxies might undergo bursts of intense star formation, driven by gas inflows or mergers, followed by quiescent periods when feedback has expelled or heated the gas, temporarily halting star formation. This bursty mode of star formation can lead to large variations in the observed properties over time, and two galaxies with the same average star formation history might look very different if observed at different phases of the burst cycle. If the high redshift galaxies observed by Webb are caught during particularly intense bursts, their luminosities and inferred star formation rates could be higher than the long-term average, and their stellar masses could be lower than suggested by their brightness, easing the tension with models. However, verifying this requires either observing the same galaxies at multiple epochs to see the variability, which is impractical given the timescales involved, or observing large samples of galaxies to statistically characterize the distribution of properties and infer the typical burst parameters. The large samples required for such statistical studies are beginning to be assembled by Webb, as multiple deep survey programs accumulate data on thousands of high redshift galaxies. These surveys will map out the luminosity function and stellar mass function at high redshift with much better statistics than previously possible, reducing the impact of cosmic variance and allowing more robust comparisons with models. Early indications from these surveys suggest that the bright end of the luminosity function, corresponding to the most luminous galaxies, is higher at z greater than 10 than standard models predict, a finding that is consistent with the individual discoveries of bright galaxies, but now quantified across the full population. The exact magnitude of the excess depends on how the data are analyzed and what assumptions are made, but the trend is clear across multiple independent studies. The comparison with simulations is complicated by the fact that simulations make predictions for the dark matter halo mass, function, and then use models to convert halo mass into observable galaxy properties, and this conversion involves all the uncertain astrophysics discussed earlier. Different simulation projects use different subgrid models and calibrations, and they can produce somewhat different predictions for the high redshift galaxy population even when starting from the same cosmological parameters. Some of the most recent simulations, run specifically to compare with Webb data, have experimented with different assumptions and found that modest changes to the star formation efficiency or feedback can bring the predictions closer to the observations, but no single set of changes has yet been found that matches all the data without creating problems at lower redshifts where the models were previously successful. This has led to speculation that galaxy formation physics might be redshift dependent, with the efficiency of star formation or the strength of feedback varying over cosmic time in a way that is not captured by current models, which typically assume that the subgrid parameters are constant or depend only on local properties like gas density or temperature, not on redshift explicitly. If the conditions in the early universe, such as the radiation background, the metallicity, or the turbulence, were sufficiently different, it is plausible that the astrophysics operated differently, and building models that capture this evolution is an active area of research. Alternative cosmological models, while less favored by the community, are also being revisited in light of the Webb observations. If the lambda CDM model is wrong in some fundamental way, if dark energy behaves differently than assumed, or if there are additional components to the universe's energy budget, the expansion history and the growth of structure could be different, potentially allowing more time for galaxies to form or altering the timeline in some other way. The lambda CDM model is supported by a vast array of observations beyond galaxy formation, including the cosmic microwave background, the large-scale distribution of galaxies, the abundance of galaxy clusters, the properties of the Lyman alpha forest, and the observed acceleration of the universe's expansion, so any alternative model must also explain all these other observations, which is a very stringent requirement. Most alternative models proposed so far either fail to match some of these observations or require fine-tuned parameters that are not well motivated, so while they are being explored, they are not yet widely accepted as solutions to the early galaxy problem. The observational program to further investigate these high redshift galaxies is ongoing and expanding. Webb has multiple large survey programs approved for its first cycles of operation, and these programs are systematically imaging and obtaining spectra of thousands of high redshift galaxies, building up the statistical samples needed to robustly test models. The surveys cover different fields and use different strategies, some targeting known overdensities or gravitational lensing clusters to find the faintest objects, others targeting blank fields to measure the average properties, and the combination of these approaches will provide a comprehensive picture of the high redshift galaxy population.